Parallel operation of transformer. Today's session will see the load sharing between the transformer they are connected in parallel. The first case we will look into how the load is shared between the two transformer if their voltage ratios are equal. Okay, I am connecting the two transformer in parallel with the first transformer has got RA and XA, that is the resistance and reactance referred to the secondary side of the transformer here. Similarly, RB and XB are the resistance and reactance, that is the equivalent resistance and reactance of the second transformer. They are connected in parallel. They are connected in parallel. They are supplied by, that is, it is connected to secondary. Here you are considering equal voltage ratio, therefore E2 for both the transformer they are the same, therefore I am replacing my single source with E2, and however the representation of these two transformers are connected in parallel. Then the load shared by the transformer A is IA, whereas the transformer B is IB, and the total the current supplied to the load is I. I is nothing but it is a vector sum of IA plus IB. Then across the load terminals, the voltage available is VL, that is what we are calling is voltage across the load, that is VL. Okay. Now, in this the circuit diagram, what is the value of the load shared by the current by the transformer A, and what is the load shared by the transformer B, that we have to look into. Then we know that this parallel circuit, the characteristics of the parallel circuit means the voltage across the parallel branches are equal. That I am considering as the V. Suppose if you are replacing this the parallel combination resistance and reactance into single the impedance, that is what we are calling is Z. That is whole the network, that is the parallel combination of these two branches can be reduced with a single the impedance, that is Z. Therefore, what is if we are reducing to one single impedance instead of two, then what is the current which is flowing in that? That is I. That is whole network, that is this parallel combination is replaced by single impedance, that is Z. You have to calculate what is the equivalent impedance of these two parallel branches, that is 1 by, that is the reciprocal of 1 by ZA plus 1 by ZB. Now, ZA is nothing but it is a resistance and reactance of the transformer A, whereas RB and XB are the equivalent impedance and reactance of the RA and XB are the resistance and reactance of the transformer B, that is represented by impedance of A and impedance of B. It is referred to the secondary side. It is equivalent impedance. Then by the identity we know that we are considering the voltage across this parallel combination is V. Then you consider one branch at a time. What is the current which is flowing in this branch? It is IA, and what is the impedance offered? ZA. Therefore, IA into ZA must be equal to V. Similarly, if you consider the second branch, what is the current flowing through this? It is IB. And what is the impedance offered by this particular branch? That is ZB. What is the voltage across this branch is also V. Therefore, V is equal to IB into ZB. The same thing I am writing here. It is IAZA is equal to IBZB, that is equal to I into Z. That is what I am calling is V, because I am considering this voltage as V. And if you are replacing this by equivalent impedance, that are what I am calling is Z. If you are combining to only one branch, in that case the current is I only. Therefore, I into Z is equal to IAZA is equal to IBZB. At the same time, you can see here I is the sum of IA plus IB. I is equal to IA plus IB. And Z is the equivalent impedance of the two transformer given by, we are finding it, that is Z is given by ZA ZB divided by ZA plus ZB. That is, this whole parallel combination is replaced by Z. In that case, the value of Z is ZA ZB divided by ZA plus ZB. Then can apply that simple the Ohm's law for this. Just what I am doing here is, if the terminal voltage is VL, that is voltage across this is VL, and what is the VL? VL is nothing but I into ZL, that is the load impedance multiplied by I is nothing but I into ZL is nothing but your PL. Okay. Then this I, that is current I, which is supplied by both the transformer A and B put together. Okay. Now the PA is, that is what is the load shared by the transformer A? The load shared by the transformer A is nothing but, that is the real part of product of voltage and IA. V into IA, that is the real part of V into IA, gives the power supplied by the transformer A. The imaginary part of product of V and IA gives the reactive power. The imaginary part of V into IA gives it is the reactive power supplied by the transformer A. Similarly, what is the power supplied by the transformer B? The power supplied by the transformer B is nothing but it is a product of voltage and the product of IB and the real part of that. That is, the real part of V into IB gives the real power supplied by the transformer B, and the imaginary part of V into IB gives the reactive power supplied by the transformer B. That is, you have to find out what is the value of IA and what is the value of IB, because the value of V is known, that is given by I into Z. Okay, now we will derive the equation for IA and IB. Just you have to apply. What is the voltage across branch A? That is a V. What is the impedance of this branch? ZA. Therefore, IA is equal to V divided by ZA. Then V is nothing but it is I into Z. Therefore, I am substituting instead of V, it is I and Z. ZA is as it is. Just I am taking I outside here and Z by ZA. Then what is Z? Z is ZA ZB divided by ZA plus ZB. Just I am substituting the value of Z in this equation. What I am getting is, it is I as it is, and this Z is ZA ZB divided by ZA plus ZB, and in the denominator I have what as ZA, I have what as ZA. Here this ZA and ZA get cancelled, then what I am getting here is IA is equal to I into ZB divided by ZA plus ZB. It is very simple. Start with the basic. V is equal to, that is one branch at a time. V is equal to IA into ZA, therefore IA is equal to P by ZA, where V is I into Z and Z is equal to ZA ZB divided by ZA plus ZB. Just you have to substitute and you have to simplify, then you are getting the current supplied by the transformer A. Similarly, you have to apply for the B. What is here the equation? V is equal to IB into ZB, therefore IB is equal to P by ZB. P by ZB. Once again, I am substituting V is equal to IZ, and once again I am taking I as a common here and Z and ZB as it is. Then I am substituting the value of Z in this equation, that is ZA ZB divided by ZB ZB, and once again this ZB and ZB get cancelled. Then the current supplied by the transformer B, IB, what I am getting here is I is equal to ZA plus ZA divided by ZA plus ZB. Then once we know the value of IB and IA, then we know the value of V, then the product of V and IA gives the total apparent power supplied by the transformer A. If you want a real power, that is a real part of V into IA gives the power supplied by the A, and a real part of V into IB gives the real power supplied by the transformer B. This is how we have to derive the equation. For that, if you are drawing a vector diagram, that is the voltage across the terminal is taken as a reference. First, then the current IA is supplying the load with the power factor of 5. Then to this VA I have to add IARA, which is parallel to I. Then I have to add IAXA to the IARA, which is perpendicular to I. Then what I am getting here is the total applied voltage E2. Similarly, VL is the terminal voltage and the current supplied by B lags VL by an angle of phi B. Now I am adding the drop of the IB. That is, one is IA, IBRB and another one is IBXB. That is also yields the same result because we are taking equal ratio, that is VL plus IAR and IXA drop is equal to also E2, and at the same time VL plus IBRB plus IBXB drop is also, you are getting the value is the E2. Okay, this is how we have to draw the vector diagram. And sum of I and IB, what I am getting is the total current, that is I. Then if we are taking, that is the IL into RL, that also gives the same thing, that is the product of IL and IL into RL, that is a voltage drop or the voltage drop across the load, that is parallel to the IL, then add IL XL, then what I am getting is the E2 once again. This is how you have to draw the vector diagram when the transformer is drawing the power supply and supplying to the load with the equal voltage ratio. These are some of the points you can remember. The total voltage drop inside the transformer V, but the current I and IB are forced to have a different phase angle due to the difference in the internal power factor angle phi and phi. Okay, because of the different power factor, the drop is remains same. The sum of the drops, that is IRA plus IXA, that is the vector sum of both the drops must be equal to the same thing. Okay. Then we will derive the equation for the unequal voltage ratio. Here, unequal voltage ratio means the secondary voltage is differ from the two transformers. Yes, you can see here. Previously, you are connected here and you have got connected one source because E2, because the induced voltage, the secondary of both the transformers are same. Therefore, they are having the same value. Therefore, the two sources are replaced by a single source. But that is not the case in here because these are unequal. However, these two transformers are connected to the load, and however the primary, this side, that is source side, it is connected to, one is connected to EA, another one is connected to EB, because we are considering here the unequal ratio transformers. The same thing is written here. I told you in the one of the classes, that is, one may not be able to get two transformer of the identical voltage ratio in spite of one's best effort. You want to try to build two similar transformer, it is not possible due to manufacturing differences. Even in the transformer built as per the same design, you are having the same design, same material, but the voltage ratio may not be the same. In such cases, the circuit representation of parallel operation will be different as shown in the figure. This is how we are representing the two transformers are connected in parallel with different voltage ratio. Now once again, the current supplied by the transformer is I, B is IB, and total current supplied to the load is I, and the RA and XA are the resistance and reactance of transformer A, RB and XB of the transformer B, and EA and EB are the induced voltages across the secondary of the transformer. Then, how we are go about the calculation? In this case, the two input voltages cannot be merged to one as they are different. Okay, that is I told you. The load being about a common connection at the output side, that is why it is common, load is common, therefore we are shorting here, it is connected to load. EA and EB are the no load secondary EMFs. ZL is the load impedance at the secondary terminals. Then you have to interrelate the voltage relation between EA and VL and EB and VL. How exactly you are representing? That is, EA is nothing but it is a voltage across the load plus voltage drop across the transformer A, that is VL plus IAZA, that gives EA, where VL is nothing but it is I into ZL, because load impedance is ZL, that is I into ZL. Therefore, V can be replaced by VL can be replaced by I into ZL. Similarly, I have got a EA, I can write as I know what is the value of I? I is IA plus IB. Therefore, I am putting instead of I, it is IA plus IB into ZL plus IZA as it is. Similarly, you have to write the equation for V, that is EB is equal to VL plus IB ZB, that is EB. This EB is equal to VL plus IB VL plus IB ZB. Once again, VL is nothing but I into ZL, IB ZB as it is. Then I can be replaced by IA plus IB into ZL plus IB ZB. This is how we are getting the voltage of EA and EB. If you are solving these two equations, then we are getting the what is the current shared by the transformer A and B. How exactly these are sharing the load, we will see here. I am taking the same equation, EA is equal to IA plus ZL for the first transformer, EB is equal to IB ZB plus IA plus IB into ZL. The same equation what we have seen here. It is based on, it is VL plus IA ZA is equal to EA, EB is equal to VL plus IB ZB, where VL is nothing but I into ZL, and at the same time I is equal to IA plus IB. The same thing replaced, and we are getting the equations here. Then I am taking the difference of these two equations. What I am getting is EA minus EB, that is, if you are EA minus EB, if you are taking IAZA, IA plus IBZL, IA plus IBZL get cancelled. What I am getting is IAZA minus IBZB. Then from this equation, I am calculating the what is the value of I. That is, what I am getting is IA is equal to EA minus EB. This IBZB I am transferring to that side. Therefore, I am getting here this plus IBZB. Then it will come in the denominator ZL. Just have to simplify this, and we are getting the value of I. This is one part. Just have to take EA, EB, take the difference. From that you have to find out I. Keep it one side. Next, then I am taking the second equation, EB is equal to IBZB, IA plus IB into ZL. Okay, just you have to do how I am calculating the value of IB. Okay, that is what I am taking all the B parameters I am taking to the left hand side. EB it is there, IBZB I am taking the left hand side. Then here I am getting IB into ZL, that is the right hand side I am bringing to the left hand side. It is minus IBZL, that is equal to ISZL. Then once again what I am doing here is, in the value of I am substituting the value of this. Just I am showing here. I am substituting the value of I. Therefore, what I am getting is, I am taking the negative sign throughout, that is minus EB, this become plus, this become plus, this become negative, this become negative. Okay, once again I am simplifying that. What I am getting, that is I am taking IB common from this. I am taking IB common from this. That is, I am taking IB here, that is ZB plus ZL. Here in the right hand side, what I am getting is, it is IB, ZB and ZL divided by A, that I am bringing to the left hand side. This is what I am getting. Therefore, simplifying this, then what I am getting is this value. Okay. Then find out from this what is the IB. IB is equal to EBZA minus EA minus EB into ZL, what I am getting, and the numerator is ZA, ZB, ZL, ZA, ZB, ZL. In the same fashion, you can write the equation for the value of I. That is, instead of EB into ZA, it is EA, ZB. Instead of plus or minus there, it is plus, it is EA minus EB divided by ZL. Divided by the same thing, ZA, ZB, ZL, ZA or ZB, ZL. Okay, this is how you have to derive the equation for load shared by the transformer. One is simple IA, then you have to start with the EB, then go on substituting the value of IA in here, then simplify for IB.